Hello everyone and welcome to the lecture today. Today we'll be talking about the simplest type of ODE system that we could obtain, which is a linear system of constant coefficients. We went over in the last class the variation of constants formula in general for first order systems, but today I really want to kind of dive deep into how to obtain the fundamental solution set to a linear system of constant coefficient ODEs. This will, in a very real way, end up giving us some ways forward towards approaching non-constant coefficient ODEs, and also how to classify critical points in general for nonlinear systems as well. So a deep understanding of linear systems of constant coefficient ODEs is vital to really understanding stability of critical points for many nonlinear systems. So what we mean here by a first order system of constant coefficient IVP or ODEs is a system where xi prime, xi itself is a vector valued function of n dependent variables, all dependent on t, and xi prime is equal to a times xi, where a is a constant n by n matrix. And we will also have an initial condition, xi of t naught is equal to xi naught. Let's say this is for t in some interval from a to b, which we'll call I a little bit later on. So what we will see is that the solutions of this type of system of first order ODEs are very, very, very closely linked and dependent on the eigenvalues and eigenvectors of the matrix A. So this is a little bit of a review from linear algebra. So that A, elements of which are Aij for I and j from 1 to n. So we let A be a constant n by n matrix. The eigenvalues of A are any real or complex numbers lambda for which the matrix equation A minus lambda times I times U is equal to 0 vector So this algebraic system of equations has at least one non-trivial solution, U. And in general, we will have multiple eigenvalues, and for a given eigenvalue lambda, we call the corresponding solution U the eigenvector associated with lambda. And you could ask, why are the eigenvectors and eigenvalues of A, which you hopefully have a decent amount of practice from your linear algebra class computing, you might ask why these are important to solving this constant coefficient linear system. And what I'll ask you to do is, consider an eigenvalue lambda along with the corresponding eigenvector U, which we call the eigenpair, or an eigenpair of A. So assume lambda is the an eigenvalue and U is an eigenvector associated with A itself, the constant matrix A. And then consider the following combination. Consider the vector function y of t that's defined as e to the lambda times t times the eigenvector u. If you take the derivative of y of t, U is constant, lambda is constant, so this just becomes lambda times e to the lambda t of u. This holds whether the eigenvalue is real or complex. You can show this. And this is the same thing as lambda times the matrix I, the identity matrix, times u e to the lambda t, which from the definition of the eigenvalue-eigenvector relationship, lambda times I times u, is the same thing as A times u times e to the it, or e to the lambda t, which is equal to A times y, because y is the product of u and e to the lambda t, which means that for an eigenpair of the matrix A, y of t satisfies this differential equation right here. So this clearly shows, why knowing all of the different eigenvalues and eigenvectors of a given matrix A is fundamental to going through and forming the fundamental solution set of linearly independent solutions to a given system of differential equations. And we will start with a study of what happens when we have n linearly independent eigenvectors, and subsequently prove that when whenever we have distinct eigenvalues, we will have distinct linearly independent eigenvectors. At the very end, we will go over what happens when this is not the case, which is a distinct possibility. But let's start with discussing distinct eigenvectors, or eigenvalues. We'll see that really all we need is to have n distinct eigenvalues. Suppose that the matrix A has n linearly independent eigenvectors u1 to un, and let lambda I be the eigenvalue associated with or is corresponding with is probably a better eigenvector ui. The fundamental solution set is the set of functions e to the lambda 1 times u1 e to the lambda 2 times t. Oh, that's important. You need times t up here times u2 all the way up to e to the lambda n times t un. And so the fundamental solution matrix is the matrix formed by taking each one of these fundamental solutions as a column of the matrix. For the homogeneous system, psi prime is equal to a xi. And all we need to show here to prove this is that the Wronskian is non-zero. And the Wronskian, so we'll call each one of these fundamental solutions xi1, xi2, xi, or actually instead of xi, let's use phi, lowercase phi, like we did in the last lecture. This is phi1, phi2, all the way up to phi n. So the Wronskian of this fundamental solutions matrix as a function of t will be the determinant of this matrix formed by phi1 to phi n, which is the determinant of this matrix, and one of the major properties of determinants from linear algebra is that if you have a multiplicative constant in one of the columns of the matrix you're taking the determinant of, that will come out of the determinant as a multiplicative constant on the entire determinant. So we can do this for each one of the columns. This will be e to the lambda 1t times e to the lambda 2t all the way up to e to the lambda nt times the determinant of u1, u2 to un. And because the UNs are all linearly independent, this determinant is non-zero, and we can rewrite this a little bit simpler. This multiplication of exponentials is the same thing as e to the sum of all the eigenvalues times t times this determinant. And this exponential will never be zero, non-zero, for any value that we put in this expression. And as well, this determinant is non-zero because of the fact that u1 and u2 and all the eigenvectors are linearly independent. So the Wronskian is not, this Wronskian of this fundamental solution set is never zero. And this allows us to go through and compute the, using this fundamental solutions matrix for our system of first order differential equations with constant coefficients. Now things will get a little bit more tricky when we don't have n linearly independent eigenvectors, but we have the following theorem that will guarantee that we will always have linearly independent eigenvectors if we have distinct eigenvalues for the matrix A. So if lambda 1 to lambda n are distinct, which means different numbers, possibly real or complex eigenvalues, for the matrix A, or of the matrix A, and ui is the eigenvector corresponding to lambda I, then the set of vectors u1 to un is linearly independent. And to prove this theorem, I'm just going to prove the general case when m equals 2. The specific case when n equals 2, but you can hopefully very clearly see that this can be easily extended to the case when m is any higher integer. So we're going to do a proof by contradiction for n equals 2. Suppose u1 and u2 are linearly dependent, where lambda 1 and lambda 2 are distinct. Eigenvalues so if u1 and u2 are linearly dependent, that means that u2 can be written as some constant times u1. In which case, we can multiply both sides of this equation by the matrix A, and apply the eigenvector relationships for the eigenvector eigenvalues, or the eigenpairs, lambda 1 u1, lambda 2 u2, to get lambda 1 times u2, or lambda 2 times u2. And c times lambda 1 u1. We can also multiply both sides of this expression by lambda 1 to get lambda 1 u2 is equal to c lambda 1 times u1. So I'll call this equation 1 and this equation 2. And if I subtract equation 2 from equation 1, I get a cancellation. Specifically, I get that the right-hand sides of both equations cancel out, and I'm left with lambda 1 minus lambda 2 times u2 is equal to the 0 vector. And since u2 is an eigenvector, u2 is not zero vector, which implies that lambda 1 is equal to lambda 2, which is a contradiction. We're contradicting our assumption that lambda 1 and lambda 2 are both distinct eigenvalues. So therefore, we've proven the case, our theorem for the case n equals 2, for n greater than 2, the result follows from induction, mathematical induction. Which is a proof technique typically gone over in a discrete mathematics course. But so, armed with this theorem now, we have that if we have distinct eigenvalues, for a constant coefficient linear first order linear system, we have the direct form for the fundamental solutions matrix, or the fundamental solution set. This is a corollary of the theorem, previous theorem, that if A has n distinct eigenvalues, lambda 1 to lambda n, and ui is the eigenvector correlated or associated with, say, corresponding to in the fundamental solution matrix is the matrix that we listed before. With phi I being equal to e to the lambda I times t times the eigenvector ui. And this also gives us a set of n linearly independent solutions. So let's go through and look at a couple of examples. This first example will indicate what happens when we have distinct real eigenvalues. This will be the differential equation. Xi prime is equal to 0, 1, negative 2, negative 3 times I. The first step is to write down the characteristic polynomial. This will be P of lambda. Matrix A here is this matrix. is the determinant of the matrix A minus lambda times I, which will end up being negative lambda times negative 3 minus lambda minus negative 2 times 1, which will end up being lambda squared plus 3 times lambda plus 2, which factors to lambda plus 1 times lambda minus 2. If it doesn't factor nicely, we have to go through and use the quadratic formula here, but it does in fact factor nicely. So then step number 2 is to determine the eigenvalues. These are when p of lambda is equal to 0. Oh, there should be a plus right here. So the eigenvalues correspond to lambda 1 equals negative 2, and lambda 2 equals negative 1, because those are the two roots of this polynomial equation. Step 3 then will be to construct the eigenvectors and the eigenvectors so of an eigenvector for lambda 1, so we'll say this is AU is equal to lambda 1 times u, and we'll have an eigenvector v for lambda 2. So we have to solve the equation AV is equal to lambda 2 times v. This is a matrix A, which is 0, 1, negative 2, 3. Is equal to negative 2 times u1, u2. And the matrix 0, 1, negative 2, 3 times v is equal to negative 1 times v1, v2. And so going through and solving for the eigenvector u1, u2, you solve this system for u1, u2, you solve this system for u1, u2, you see that any eigenvector, when we solve this system of, so any eigenvector of this matrix A corresponding to negative 2 is going to be of the form of a constant times the vector 1, negative 2, and any eigenvector v is going to be of the form of a constant times the vector 1, negative 1. So we're free to choose which one of these eigenvectors, any value of s here and any value of s here, but the easiest choice is typically s equals 1. And so this means that our fundamental solution set is phi1 of t is equal to e to the lambda 1 times t times the vector u, which is equal to e to the negative 2t times the 1, negative 2, and phi2 of t will be e to the lambda 2 of t, or e to the lambda 2 times t times v, which is e to the negative t times the vector 1, negative 1. Which means our general solution for this example will be c1 e to the negative 2 times t times the vector 1, negative 2 plus c2 times e to the negative t 1, negative 1. Which is the general solution to the homogeneous problem. Now, to specify an initial condition, we can go through and satisfy this by plugging in the initial condition, which is xi of t naught is equal to xi naught, which becomes equivalent to c1 e to the negative 2t naught plus c2 e to the negative t naught. You have negative 2 times c1 times e to the negative 2t naught plus negative 1, so minus e to the negative t naught times c2 or the fundamental matrix evaluated at t naught, e to the negative 2t naught, e to the negative t naught, negative 2 e to the negative 2t naught, negative e to the negative t naught times the vector of unknown coefficients c1, c2, which is phi of t naught times the unknown coefficient vector c. To solve for the coefficients, we would take the inverse of this matrix and multiply it by the initial condition vector xi naught, or phi naught. Which is exactly the initial coefficient matrix, or the coefficient matrix c1, c2. The exact expression appears in the variation of constants formula that we talked about before. So this is very cool. This is giving us a definitive way of going through and solving linear constant coefficient systems. And the next example I want to go over is what happens when you have complex eigenvalues. But before I do that, we're going to need a theorem. This is that if xi is equal to xi1 plus I times xi2, so if the solution xi is a complex vector valued solution of xi prime equals a xi, homogeneous linear differential equation with constant coefficients, then xi xi1 and xi2 are real vector valued solutions of the homogeneous equation star H. And I should specify here too. So if xi equals xi1 plus xi2, it's a complex vector valued solution of star H and xi1 and xi2 are real vector valued functions then xi1 and xi2 are also real vector valued solutions of star H. The proof of this is relatively straightforward. We know that xi prime is equal to the matrix A of T times xi, and this actually holds for more generally if you have a homogeneous differential equation with depends on T, so even non-constant coefficients. So let's make that explicit here, that A of T could also depend on some T. So if xi prime equals A of T times xi, we know that this means then that xi is this complex vector valued function, where xi1 and xi2 are real vector valued functions. So this will be xi1 prime plus I times xi2 prime, where I is the imaginary unit. And A of T times I will be the matrix A of T times xi1 plus I times xi2. So this expression can be rewritten as the matrix A of T times xi1 plus I times A of T xi2, and because xi1 is a real vector valued function, xi2 is a real vector valued function, and A of T is a matrix of real coefficients, we have to equate the real and the imaginary parts of these two complex vectors. So we have to conclude that xi1 prime is equal to A of T times xi1, and that xi2 prime is equal to A of T times xi2, or T and I. So let's go through and consider the following example. We'll consider the linear system. Xi prime is equal to the matrix -1/2, 1, -1, negative 1/2 times I. Or this is our matrix A. Step 1 is to set up the characteristic polynomial P of lambda, which will be the determinant of A minus lambda times the identity matrix, which will be negative 1/2 minus lambda times negative 1/2 minus lambda minus negative 1 times 1. Which results in the characteristic polynomial being 1/4, which is negative 1/2 times negative 1/2, plus 1/2 times lambda, plus 1/2 times lambda, plus lambda squared, plus 1, which is the quadratic polynomial lambda squared plus lambda plus 5/4. The eigenvalues are the roots of this polynomial. So when P of lambda equals 0, where this is going to be by the quadratic formula, and lambda is equal to negative b plus or minus the square root of b squared minus 4 times a, which is 1 times c, divided by 2 times a. So the eigenvalues will be negative 1/2 plus or minus 1/2 times the square root of 1 minus 5, which is negative 1/2 plus or minus the square root of 4 times I, because we have the negative value under the square root. And so the eigenvalues are lambda 1, which is negative 1/2 minus the square root of 4 over 2 times I, or just 2 over 2 times I, which is just I, and lambda 2, which is negative 1/2 plus I. The eigenvectors are going to be complex, because the eigenvalues are complex numbers, but they're still going to satisfy the eigenvector equation. A times u is lambda 1 times u, and A times v is lambda 2 times v, which can be solved using standard methods from linear algebra. So you can solve a given system like this in many different ways. The easiest way is probably using the reduced row echelon form, but you have to remember that these values are going to in general be complex. This is going to give us the equation negative 1/2 1 negative 1 negative 1/2 times u is equal to negative 1/2 minus I times u1, u2 and A is negative 1/2 1 negative 1 negative 1/2 times V is equal to lambda 2, which is negative 1/2 plus I times V. So when we go through and solve this, you get this will be negative 1/2 u1 plus u2 is equal to negative 1/2 minus I times u1 and you also get negative 1 times u1 minus 1/2 u2 is equal to negative 1/2 minus I times u2. And again, I want to emphasize that for larger systems, you can go through and use row reduction to solve for the eigenvectors. But for smaller 2x2 systems, sometimes it's easier to see the solution just by going through and doing one of your standard solution methods. So substitution or elimination, right? These are all procedures that can be used to solve this system. But ultimately what happens is that you get that the eigenvector when this is solved is of the form S times the vector I1, and you get that the eigenvector V is of the form S times negative I 1. And so the eigenpairs for this system are this eigenvalue with this eigenvector and this eigenvalue with this eigenvector. So the general solution then is I of t will be of the form c1 e to the lambda 1 times t times u plus c2 e to the lambda 2 times t times v. So I of t will be equal to c1 e to the negative 1/2 minus I times t times u plus c2 e to the negative 1/2 plus I times t times v, which is negative I 1, and I'll put in u as well. The vector I1. And we have to do a little bit more now because, from this theorem, we can go through and actually get a solution that is in terms of only real numbers by cleverly rewriting this expression. But we have to go through and do that right now, and because this is not in the form, xi here is not in the form of xi1 plus I xi2, whereas xi1 and xi2 are real. Luckily, this will be possible to go through and do directly. Now, before going through and trying to simplify this, let's kind of take a long, hard look at what exactly we have so far. So here we have two fundamental solutions. The first is phi1 of t is equal to e to the negative 1/2 minus I times t times the vector 0, 1 plus I times 1, 0. And phi2 of t is e to the negative 1/2 plus I times t times the vector 0, 1 minus I times 1, 0. In general, when we have a pair of complex eigenvalues and eigenvectors, this is going to be what we see. So what I'll do is, do the general simplification below. Let's suppose that lambda 1 is some alpha minus beta times I, and lambda 2 is some alpha plus beta times I, and the corresponding eigenvectors u and v are going to be some real valued vector A minus I times b for some b. So A and B are real valued, and V is going to be some A plus I times B for some real valued A and B. And the idea here is the following. So we'll just consider how we can simplify phi1 of t. We can rewrite it as e to the negative alpha t times e to the negative I times t, or times beta t, times A minus B times I, and likewise phi2 of t is going to be equal to e to the alpha t this should be e to the alpha t times e to the I times beta t times A plus B times I. And both of these can be simplified using what's called Euler's identity, or Euler's equation, Euler's formula. This is one of the most fundamental formulas in all of mathematics. I go through and I prove this for my Calculus 3 students. This is that for any real value theta, e to the I theta is cosine of theta plus I times sine of theta. So using this formula for phi1 gives us e to the alpha t times cosine of beta t minus sine of beta t times I times A minus I times B. And for phi2 of t, we have e to the alpha t cosine of beta t plus I times sine of beta t times a minus a plus b times I Now let's go through and see what both of these simplify to. By foiling out, this will become cosine of beta t times A this times this plus sine of beta t times b plus or minus I times cosine of beta t times b plus sine of beta t times A. And for p2 of t, this is going to be cosine of beta t times A minus sine of beta t times b, which is this term times this term, plus I times cosine of beta t times b plus sine of beta t times A. And so this is actually really incredible, because here we have that this function right here we'll call xi1 of t is a real valued function that solves the differential equation by the previous theorem. This function right here we'll call xi2 of t is also a real valued function that solves the differential equation. This expression in both cases also solves the differential equation as well, the imaginary part from the theorem that we wrote down before. However, what's special about xi1 and xi2 is that they're both real valued solutions, and what's amazing here is that xi1 and xi2 are both solutions of the differential equation, and they are linearly dependent. Now would be a good exercise to go through and show that. So I recommend going through and doing that. But because of that, we can take xi1 and xi2 as fundamental solutions to our differential equation, and therefore our general solution, xi of t, can be written as c1 star times xi1 of t plus c2 star times xi2 of t, where c1 star and c2 star are new constants, not related to c1 and c2 from before. I mean, you can go through and try and get the exact relationship, but really we don't need to, because we know that if we have two linearly independent solutions to our 2x2 system, then we'll be good. This procedure right here that I just showed directly applies to higher dimensional linear systems as well, because eigenvalue eigenvector pairs that are complex will always appear like this, which is very, very cool. And what that means then is that the general solution to our differential equation is going to be c1 star times xi1 of t which is this vector function of t oops, we need the e to the alpha t here as well. Plus c2 star times xi2, which is this function right here. This is a little aside that I wanted to do to show that it's always going to be possible to go through and get this solution using these fundamental, the original fundamental solutions. In this example, our A is the vector 0, 1. And our B is the vector this has to be, say, minus b, which is minus -1. This will be plus -1. So b is the vector -1, 0. So the general solution to this differential equation will be c1 star times e to the -1/2 times t times cosine of beta t times 0, 1 plus sine of beta t, or beta here is 1, so it's just t, and t right here times -1, 0 plus c2 star e to the -1/2 t times cosine of t 0, 0, 1, and then minus sine of t times -1, 0. or xi of t is equal to c1 star e to the negative 1/2 times t times the vector negative sine of t cosine of t plus c1 star e to the negative 1/2 t times positive sine of t cosine of t. Which is very neat. And so if this satisfies some initial condition, which we have an initial value problem, so in general it'll satisfy some initial condition, xi of t naught. This will end up being c1 star e to the negative 1/2 t naught negative sine of t naught cosine of t naught plus c1 star e to the negative 1/2 t naught times sine of t naught cosine of t naught. Which is the same thing as the matrix e to the negative 1/2 t naught negative sine of t naught cosine of t naught. The first column in the matrix is this, and the second column in the matrix is e to the negative 1/2 t naught times sine of t naught cosine of t naught times the vector c1 star c2 star. So this is the fundamental solution matrix. I'll call it psi, capital psi star, or capital psi of t naught, because it's the real fundamental solution matrix multiplied by the vector c1 star, c2 star. So to solve for the coefficients c1 star and c2 star, you have to find the inverse of this matrix or solve this system for c1 star, c2 star. And because the columns are linearly independent from one another, this matrix is invertible. We can find the inverse. And this matrix inverse multiplied by both sides of this equation gives you the solution for c1 star and c2 star as the inverse of this matrix multiplied by the initial condition, xi naught. So this is very cool, and we've now seen how to deal with distinct real or distinct complex eigenvalues. What we're going to move into in the second half of the lecture will be how to deal with repeated eigenvalues, which is the last case that you see when you go through and solve linear systems with constant coefficients.